Okay, we're going to do it's going to be a little bit of a review, but we're really going to start looking at atmospheric circulations, and we started that with Coriolis effect. We started that with the global winds, but this is really getting into what is Coriolis effect and why those winds break where they do. So, quick review. Again, this is obviously important because I'm going through it for about the eighth time. We're talking about conduction, convection, radiation. So, the transfer of heat. The sun has radiation that hits our ground, and heat is actually radiated up, but also the air that's in contact with the ground gets warmer because as the ground absorbs all that energy, it heats up. In fact, ground will heat up much faster than water. It will also cool down much faster than water, which will lead us to another kind of wind that happens later. Those are land breezes and sea breezes. But right now, let's just talk about basic atmospheric circulation. So, as this ground heats the air, hot air is less dense and it tends to rise. And you know that it rises at a rate of temperature loss at about 5.5 degrees for every 1,000 feet until it hits its dew point, and then that's 3.5 degrees for every 1,000 feet. So as it cools, it becomes more dense and eventually starts to sink, and we get these convection currents: cold air sinking, warm air rising. Really basic things. So you would expect that on our Earth, the hottest area would be at the equator and the coldest area would be at the poles. And it's true, we have hot air rising at the equator and cold air rising at the poles. And so this is what we would expect to see. We'd see one big high pressure cold system at the North Pole and the South Pole, and a huge low pressure system, hot rising air at the equator. But because the Earth spins underneath it, it doesn't just stay that way. In fact, we get those Hadley cells, and we have one at breaks at 30 and 60. So we actually have 3 cells north of the equator and 3 cells south of the equator. And because of that turning, we get more than one cell. Here's our Hadley cell. It rises, it condenses its water out, we get nice cloudy air, it cools, and then it becomes more dense and cold and it sinks. But remember, as it sinks, it gains temperature at 5.5 degrees for every 1,000 feet it descends. So this air is dry because we've wrung all the water out here at the equator, and it's hotter than when it left the equator. So at 30 degrees north and 30 degrees south, we have our world's deserts because of that cold, dry air that sinks and heats up. And descending winds are not very good for sailboats. Remember, we talked about that. That's our horse latitudes. So as it hits and comes down here, the 30 degrees north actually deflects south and east. Those are the northeast trade winds. And from the south, it actually goes north. So these are the southeast trade winds. Now, the southeast trade winds are a misnomer because they actually flow north. The northeast trade winds are a misnomer because they head south, but it's a naming convention. We always name winds from the direction from which wind originates. So a north wind in your head should tell you it's going to be cold, but it heads south. So a north wind comes from the north. A south wind for us, like from the Gulf of Mexico, comes from warm areas. So this is true in the northern hemisphere. So you have to flip that if you're in the southern hemisphere. But winds are always named from the direction from which the wind originates. So these are the northeast trade winds. These are the southeast trade winds. And we have sinking air there. Now remember, our sinking air is going to also flow south from here, 30 degrees south. And it's going to flow northward from 30 degrees north. And it's going to come in with other air sinking at the poles. So global wind belts exist because the air does not simply rise at the equator and sink at the poles. That turning kind of stops it and starts it sinking earlier than the pole. And then we get our cells. So we get our sinking air at 90 and it flows south. We've got our sinking air at 30 and it flows well south and north. And when we have those two air masses collide at about 60, the only place that have left to go is up. So we have 3 distinct cells north of the equator and 3 distinct cells south of the equator. Let's take a quick look at this. Perhaps.
On a greater scale, we find regional winds affecting weather over larger areas. Generally, large land masses, or continents, heat more in the summer than large neighboring areas of water. And in the winter, this land cools more than the nearby water. These temperature shifts create wind patterns. For example, in Asia, we have monsoons, which are steady prevailing seasonal winds. So that in India, winter winds are dry, blowing from the land to the sea. But then, during the warmer months, the monsoon season, warm, moist winds blow from the sea, causing an extended rainy season.
Local and regional winds are the result of area conditions, but global wind patterns produce larger air movements. Such wind patterns are caused by the Earth's rotation and the unequal heating of our planet's surface. Receiving the sun's most direct rays, the equator has the globe's warmest temperatures, while at the planet's opposite ends, the two poles receive the most dispersed radiation, registering temperatures usually far below freezing. Because of these constant temperature differences, hot air at the equator rises and moves toward the poles, while the cooler air at the poles sinks and moves toward the equator, thus creating a continuing wind system. The Earth's rotation causes these winds to shift. Think for a moment. Which way does the Earth rotate?
We always go
The Earth
towards
rotates on its axis from
New
west
York.
to east. Because of this, the winds in the northern hemisphere curve to the right, and the winds in the southern hemisphere curve to the left. Scientists call this wind shift the Coriolis effect. To avoid being blown off course to the west in the northern hemisphere, pilots must calculate the Coriolis effect in their navigation. Generally, on continents around the world, prevailing wind patterns are westerly, going from west to east. So in the U.S., it's not unusual for California weather to be headed in a few days for New York and other eastern states. Sometimes this westerly pattern is influenced by colder air from the poles, deflected by the Coriolis effect. Severe weather is likely when this east to west wind flow occurs.
Okay, so that's getting if the polar easter. That's if the jet stream pushes down. And we know those are fun things in the winter because that's when we get our serious snowstorms, or one of the reasons. It's a good indicator. So this is actually a picture of an icebreaker at the North Pole. Remember, the North Pole does not have any land underneath it. It's Arctic ice. South Pole does. Antarctica is actually the driest continent. It's considered a desert, which is ironic because it's full of snow, but it just doesn't melt that much snow each summer, and so it builds up year after year after year. But the North Pole is actually Arctic ice, and so this was an icebreaker ship that came in, and the crew got out and they located the geographic North Pole, put a banner there that says North Pole. And so at this point, you could literally stand on that spot and spin in a circle and say you traveled all the way around the world because you faced all 360 degrees view. So, and if we're looking for the North Pole down, we go in this direction, which is counterclockwise. And that's hence the Coriolis effect, is that spinning Earth. And here's our path coming down. It gets deflected, and so we have the polar easterlies up here, and down at the equator where we have the sinking air, then from that rising air at the equator sinking at 30 degrees, it also gets deflected to basically from an east wind. It gets deflected to the left. We live in this, which is prevailing westerlies, which it gets deflected the other way. And the reason why this happens is if I had my globe in front of me, I could actually spin the globe and draw a line straight down. And if the globe was stationary, you'd see I'd get a straight line from the pole to the equator. But if I start spinning the globe underneath it and draw the line straight down, you'll notice that it gets deflected because the Earth literally drags it with us. So I made a low-tech version of that example, which is paper, so really low-tech, and a tack. And this is a North Pole view. So if I wanted to, without a rotating Earth, I could draw my line straight down and I could hit the equator. But if I start spinning it and draw a straight line, you'll see it actually gets deflected. And those are those polar easterly winds. And that's also why we have the northeast trade winds. And it's how they come down and they meet as it hits there, where it gets deflected the other way for where we are. So we live in the prevailing westerlies. That you can literally see as you try and draw a straight line on a curving planet, one that turns. You absolutely cannot draw a straight line. It's always going to get deflected, and we end up with our nice curved wind patterns. So that's the Coriolis effect. It's that rotation. So the curving of the winds due to the Earth's rotation is the definition of the Coriolis effect. So that also affects, and this is kind of a precursor for storms, our high pressure and our low pressure systems. And there's a reason now why they start to rotate in a specific direction. We talked about the fact in our last unit that high pressure cells have higher pressure towards the center, and low pressure cells have lower pressure towards the center. And they get deflected. So moving objects appear to deflect to the right in the northern hemisphere due to the Earth's rotation. An air mass of high pressure rotates clockwise due to the Coriolis effect in the northern hemisphere. And low pressure cells rotate counterclockwise in the northern hemisphere. So this is the same as our deflection of our rotation on Earth. So the interesting thing is, if I go here and I follow this wind down, because remember, everything flows from high pressure to low pressure, right? But it's spinning air, right? So I can't quite draw it that way. So let's try it again. My air is spinning out and it says high pressure, and it's like, okay, but I have low pressure here. I want to go down to there, and it gets sucked in and it rotates into the center. And then as it gets warmer and therefore lower pressure, air starts to rise. So this cold, dense air from the high pressure system runs in to fill that vacuum created, or that space created, as the warm air rises. And so this is an interaction between a high pressure cell and a low pressure cell, and it's actually curved. All right. So by the way, any of these videos, if you're having a hard time hearing them, you should stop the video and then go watch it in the actual notes. But this is just looking at our spinning Earth. And we look at this, actually, I believe we can now, I've got it so it records my whole screen. If we go to the website that that's located at, maybe, possibly. Oh. Well, you gotta love that. Flash Player is not working. So this is looking at heating patterns and drying patterns. And what we're really looking at here, as this comes around, here's Africa. And you could actually, if this was a little better, we could see those patterns. So I'm not going to spend a lot of time on that, because normally I just go here to show that. And it can show some different diagrams of wind moving across. And I apologize, I'll probably take that one out. It's no longer a good demo because we're losing flash shortly. So if we think about this, air also sinks, remember, at 30 degrees north and 30 degrees south latitudes, and rises at 60 degrees north and 60 degrees south latitudes, creating 3 convection currents in the northern and southern hemisphere. And it's those interactions where those poles come, we get jet streams. And this is kind of more of a 3D view, and this is still a precursor of starting to get into storms. But again, as this cold air sinks, because it's dense, it flows out in a clockwise direction. And if it can see a low pressure cell, it wants to go rush in and fill that in. That's rotating it counterclockwise, like the Coriolis effect. And it wants to spin in, and as it gets spun into that hot area, it starts to heat up and it starts to rise. And as it rises, it cools, and then it flows back towards this high pressure cell where it gets piled up and spins out. So you get this nice convection current thing going. And as you get that trying to balance out, if you have just the right conditions. And in the United States, we have, between the Appalachian Mountains and the Rocky Mountains, we have the right combination of information, of weather information, to all hit. And we've got moisture from the Gulf of Mexico, we've got prevailing westerlies, we've got northeast trade winds, and you've got air rising north from the Gulf of Mexico, and we can have something called tornado alleys. And we'll talk about that on another day, but that's coming up. But it still has to do with this equalizing of pressure. So as air pressure equalizes, everything flows from high pressure to low pressure. Okay. So the result in three global wind patterns in the north, in each hemisphere, north and south. We've got the trade winds; those are from the sinking air, and we've got our northeast trade winds and our southeast trade winds going the opposite direction as it flows down. So this gets deflected down to the left, and this gets deflected to the right because of the spin of the Earth. These are the prevailing westerlies, and then of course we've got our polar easterlies deflected again to the right. So if we're looking down, I'm deflecting to the right, so it's that handy dandy polar easterlies. So winds again are named from the direction from which they come from. So a west wind comes from the west, but it's heading east. Westerlies blow towards the east, but they originate in the west. So we always, a north wind starts in the north and heads south. And the jet stream, you know, we have these perfect cells, but sometimes those cells, especially between 30 and 60 degrees, can get these little funky loops. And that loop is called the jet stream. It's still flowing down, but some of it continues to go up here and gets hooked around, because it's like if you take that pen and you roll it between two things, it can start to spin. And so this side is coming underneath it up, and this side is coming from the top south, and they can start to spin, and that's our jet stream. And so you'll notice that we've got a jet stream there and a jet stream there, and sometimes we can have a one farther south. Here's our Hadley cells and our other convection cells up here. So the two global winds that are most affect the weather in the U.S. are the prevailing westerlies and that jet stream. So the prevailing westerlies are here. That's where the bulk of our weather comes from, unless you're my cousins in Florida who get the northeast trade winds, and that's the hurricanes and all that stuff. But this jet stream, as it moves north and south, as it moves north, it lets the warm, moist air come in. And as it moves south, we get that cold, dry air from the poles coming in. So the bulk of the United States is actually affected by the prevailing westerlies and how that jet stream is moving within it. If this one is hard to hear, then again, this will be the time to stop my Edpuzzle or let it run in the background and then come back to the notes and watch this.
Well, it's 7:49, time for another Ask Dirk segment.
Today's question that you sent in involves the jet stream. So, Dirk, what's the question?
Well, the question comes from Shelby from Newcastle, and her question is, it's a simple one. It's just, why is a jet stream called the jet stream? So the simple answer is, it's a stream of air that is moving faster than the surrounding air. But of course, we're not going to leave it at that. We have a lot more to talk about as far as the jet stream is concerned, because it's an important feature with our weather that we have. Now, here's a definition: a fast-flowing current of air located anywhere from 5 to 7 miles above the surface of the Earth. That's the jet stream that we have, over us. It can be upwards of, a mile to 3 miles thick. The jet stream itself, it can run anywhere from 1,000 to 3,000 miles. You can see that aircraft love to find the jet stream, because that just adds to their ability to go get there faster and, of course, use less fuel. And that's what you want, of course, this day and age. If you're going to be flying around, it helps to save on money and energy. So the jet stream, there's actually two jet streams that we're concerned with here in the northern hemisphere. You have the subtropical jet stream. That's generally to the south of the United States, but occasionally it does affect or impact the southern half of the United States, including California. We sometimes feel the effects of the subtropical jet stream. But mainly it's the polar jet stream that we're concerned with, and that we like to watch as far as the weather patterns that we have shaping up. This is really important.
And you can see this. This would be a jet stream that's allowing that cold, dense polar air come down to us. And if this shifts up, it allows this warm tropical air to come up towards us.
Because the colder air generally stays to the north of the jet stream, the warmer air to the south of the jet stream. When you have what's called a little trough or a valley, that's where we have areas of low pressure. And usually where you have that upper ridge that blows up there, you can see that's where we have the higher pressure and the warmer air that's usually associated with these two, again, areas of air to the north and to the south of the jet stream. Now, what's so important about this jet stream is it pulls along those weather systems, and this is what gives us our rain. And so we have these areas of low pressure that swing on through. As those waves come through, that's what makes a cold front. And of course, that's where we have the rain and the snow, and that's what we get during the winter months, and that's what we need a lot of. And of course, this time of year, we've been looking at conditions that have been dry for a little bit and then wet for a little bit. So this is what's going on. When we have our wet periods like we did in the month of February, we had a situation where we had a cutoff low.
And this is a little more than we need to know, but this can get cut off, and that really affects the California's weather.
Well, it's 7:49 time.
And I think that's all we're going to do for that one because I don't want to spend the whole 3 minutes on that. So again, recap of the first set of notes we did and today's. This is the definition. Trade winds. They're blowing between the equator and 30 degrees north and 30 degrees south latitude. The prevailing westerlies blow between 30 north and 60 north, or 30 and 60 south latitudes. And this is the direction, remember, the wind comes from. Wind blows from west, so it's named the westerlies. And it's really the main impact driver in the United States. The polar easterlies, the prevailing easterlies, the polar easterlies, either one is technically correct, go between the poles and 60 degrees north or 60 degrees south latitudes, and they basically have an east wind heading west. And because it's polar, it's actually kind of going in a nice circle, which helps with that jet stream formation. The jet stream then is high speed winds between 10 kilometers about 10 kilometers above the Earth's surface. They're very wide but very shallow. And yes, I see that typo. I'll fix it. No one's told me that yet. Blow from west to east between 200 and 400 kilometers per hour, and they affect the weather in the U.S. and they generally move from west to east. So when we had nuclear fallout from Japan, when they had that huge tsunami and affected their nuclear reactors, you could actually see with our Geiger counters when the jet stream came over us, because they would actually start to spike, and we could always tell if the jet stream had moved right over us because some of the radiation was falling down. It's an interesting phenomenon that happens. But one other thing you need to remember is jets. If they can find the jet stream and go with it, get a tailwind, the jet stream actually pushes it faster. So you can actually get going faster. Like if my sister used to go to Japan about once a month she used to work at Northwest Airlines, and now it's Delta. And for her, she was in tech ops, and she would have to go to Japan. And it always took longer to get there because they had to avoid the jet stream, because if you want to float into that wind, it's 400 kilometers an hour this way, and you might be going 600 that way or 200 that way, and it cancels you out. So her trips home were always quicker, because if they could catch the jet stream, it pushed the planes along faster and they didn't have to use as much fuel, and they got there because you add the two speeds together, the plane speed plus the wind speed. So her flights home were always quicker. So this is something that we're going to actually have a quiz on, so you don't have to go into the notes and do this. But I would actually say you need to be able to tell me these are the polar easterlies, these are the prevailing westerlies, these are the northeast trade winds, the southeast trade winds, the prevailing westerlies, and the polar easterlies. This 30 degrees north and 30 degrees south are your horse latitudes, and the equator is the doldrums. That's the rising air. They're not fun to do. So you can expect to see a question like that on your test. So as warm air rises, it eventually reaches the troposphere and really can't rise that much higher, and it spreads outwards towards the poles, and that is our convection currents. Again, creates the doldrums with rising air. Horse latitudes are where we have the sinking air. And remember, the horse latitudes are because if a sailing ship got caught there, it could not, it took a long time to get out. And they had horse cargo, and to save the water for the humans, they would actually push the horses overboard, and you would see, sadly, horses' bodies floating. So sailing ships along Europe into Africa, as they were heading down south, if they saw horses floating, they would know to keep sailing south on that current to get past that sinking air, otherwise they would be in trouble. So remember also, many of the world's deserts are located at that 30 degrees north and 30 degrees south. The Sahara Desert, the Great Victorian Desert in Australia, the Kalahari, the Sonoran Desert, all of these are at 30 degrees north and south latitudes. And some of it moves towards the equator, and some of it flows back towards the north. The trade winds, we've got the Gulf Stream that comes up along here and gets deflected and actually comes back and heads almost towards England and Norway. Up here, if we went a little farther, you'd actually get into Norway, and there's a place where my grandfather was from called Bergen, Norway. And even though they're much farther north than they are, because they're on the Gulf Stream, they have a climate on that little city much more like Seattle, Washington than us, even though they're farther north. And that's because of this warm water. And so as the cold water sinks, it actually flows along here. So the sailing ships could catch that river of moving water in the ocean and catch it south. And as long as they avoided the horse latitudes or the doldrums, if they went too far to the equator, they could sail all the way along here, and they would take manufactured goods, luxury items such as guns, cloth, iron, beer, and they'd sail that down to Africa. And this is that triangular trade route, that horrible time in our history, which is they would then pick up gold and ivory and spices and hardwoods and also, sadly, slaves. Then they'd catch the trade winds and sail across the ocean, and they'd hit, the Caribbean, and they'd pick up fish and livestock. They'd deposit some of those, flour, lumber, sadly, slaves, sugar, molasses, rum, and take all of those goods. And now they're bargaining and trying to get, the best money they can and sell it. And they're picking up stuff to bring back. And then they come up here and flow along with the Gulf Stream to miss the horse latitudes. And they would pick up like whale oil and lumber and furs. And they'd trade, rice and silk and indigo and tobacco. So all of these things, sugar, molasses, and hardwoods from the Caribbean. And so you can see where that stuff came from, but it all would come back then to England, and then they'd sell it and make a huge profit, and then they'd get more of the luxury goods and again start the whole triangular trade route once again. And that all happened because of economy and sailing ships. They were trying to make money, and not an excuse for it in any way, shape, or form. So remember, we've got low pressure belts and high pressure belts, and we have our jet stream that happens because of those sinking and rising air, and that really affects our weather, which is one of the next things we'll get into. So this is the equator. This is the doldrums, and they call it dull because, well, you're just going to have to relax because it's beautiful weather. It's warm, it's often sunny with a little rain, but yeah, you just sit there and relax. Go to 30 degrees north or south where it sinks, and again, both bad sailing areas, but we get our world's deserts at 30 degrees north and 30 degrees south. If you've got questions, as always, you know how to get a hold of me. But we're going to be moving on now into more of storm predictions and what happens with effects. So we're going to take a look at a snowstorm, and then in the next day, we're going to really start looking at the formation of thunderstorms.